we've got the tire pre-processed. We're ready to advance on to the next step. To do that, I'm going to open up the simulation deck that comes with the PM FlexTire example files, this clay1 underscore 6x2 meter bed. So in this case, we've got a bed of particles already pre-populated in the simulation deck, and then we can go ahead and import the OBJ file that we just created. So I'm going to import geometry, select the OBJ file that was generated, and I'll set the units to millimeters. Okay, and there we've got our tire model brought in to EDEM. And then the question is, how are we going to define the motions of the tires? We've got two options to do this. One, to define all of the motions in EDEM alone and run just an EDEM simulation. This is the simplest and quickest option, but there are some limitations with this approach. Alternatively, we can define a simulation in which we're coupling EDEM with a multi-body dynamic software, for example, MotionSolve, Altair's MotionSolve, to define a more complicated motion or independent motions of multiple tires, say on a vehicle. So when you would want to use EDEM alone to define the motion of the tire, that would be appropriate if you're doing the calibration of the inputs of the PM FlexTire model. So something like a radial deflection under load simulation or rolling resistance of a single tire. We can do that easily in EDEM on its own. And also if we're doing analysis on either a single wheel or even multiple tires attached to a fixed or rigid axle to predict things like tractive effort, soil compaction, tractive power, things of that nature, we can stay just in the EDEM environment. So how we define the motion of the tire is somewhat dependent on the application. There's a number of different ways that we can set up the motion, but all of them will typically have some normal load that we want to be applied through the tire so that the tire is engaging with the bed of particles. And to do that, we can right-click here and say add a motion and add a force controller. And the force controller that we're going to add is force in the negative Z direction. So we'll set that up as, say, something like 40 kilonewton force in the negative Z direction. All motions have a start and end time. In this case, I'll just leave it to the default, starting at 0 and ending at infinity, basically 9,999 seconds. And we can include gravity, force, but in this case, I'm happy to skip it. It's not required. Damping coefficient can be optionally included. I'm going to leave it out, but I am going to constrain this motion, and I want the motion to be constrained in the Z direction. So I'm going to set that up by inputting a 1 in the Z and zeros in X and Y. I'll also use a speed cap to limit the speed of the motion in the Z direction to a maximum of 1 meter per second. I think it's also appropriate to update the mass of the tire. I'm going to assume that it's approximately 550 kilograms, assuming that it's a rubber tire, and this is approximately a 2-meter diameter tire, a short meter wide. And so if I save this, and in the physics, I'm going to use a trick. I'm going to set the particle limits to enabled at for both the linear velocity and the angular velocity, setting the limit to 0 meters per second and 0 degrees per second for 0 to 9,999. In that way, I can get away with using a much larger Rayleigh time step than I would be able to in solving the simulation. And if I run this rigid tire, what I should expect to see here is the tire drop vertically, engage with the particles, and have no other motions. This is the way that I normally approach setting up the motions of the tire. I add the first motion, run the simulation because it runs relatively quickly, verify the response. So long as it looks reasonable, I proceed on to the next motion definition. So there's some bounce, that all looks appropriate. But ultimately we want to do more than just a vertical load. So I'm going to rewind back to 0. And in this first example, the motion that I'll set up is a controlled forward velocity. So we're going to have a fixed velocity in the global coordinate system in the negative x direction. And I will set up a motion that will allow the wheel to freely rotate. So to achieve that constant or controlled forward motion, I'm going to add a linear translation kinematic, and I'll start that at 0.2 seconds, allowing the particle to come to rest on the bed before moving forward. And let's say we're going to go something like 2.87 meters per second. And in this case, I'm going to define a vector in a negative x direction. Now, really all that is being used here is the unit vector of this. So I've offset it to the z direction, but that's really not required. I've offset it in the z direction to the center of the tire. That isn't required. We really just need a negative x unit vector with an initial velocity of 2.87 meters per second. So if I save this and come back and run the model again, it's going to have to run past 0.2 seconds. We should see the drop of the tire before the 0.2 seconds, and once 0.2 seconds is exceeded, we should see the tire start to translate in a fixed orientation in the negative x direction. And that's exactly what we're seeing here. But it's still a fixed orientation. The tire is not going to freely rotate. So I'm going to rewind back to 0. In order to get that free rotation, I'm going to add a torque controller to apply that for all time steps, starting at 0, ending at 9,999, adding no torque in the x, y, or z, leaving that all as 0. I'm not going to include the gravity in that torque calculation. I will add an angular speed cap. It's maybe not required, but to limit the velocity at which the tire would rotate to 360 degrees per second. We do need this to move with the body, and we're going to constrain this to the axis of rotation of the tire. So in this case, it would be appropriate to set, say, 1,000, negative 1,000, negative 1,000. And we very much need to set the Z offset to the center of the tire. And I'm going to set the point of action to the start point. So in this case, we've got the center of the tire. The direction of this vector isn't so important. It's going to, this tire for torque controller is going to allow for free rotation around this axis that's aligned with the Y, that's offset to 1,200 millimeters in the Z direction. And now if we save this and come over and run the model, what we should see is the tires start to rotate with a translation. There we go. You can see that the tire is now translating in the negative X direction and rotating about its own axis. So that is the process to set up a controlled forward velocity. So now let's take a look at how we would set up a controlled rotational velocity. So if we come back and rewind to the 0th time step and save it, we will continue to use the the vertical force to apply the normal load through the tire, but we're going to eliminate the constant forward speed, and we're also going to eliminate the freely rotating axis of the tire, or the torque controller of the tire. Then we'll add in a motion for a constant rotation, a linear rotation kinematic. Now in this case, let's set up the initial velocity to something like 180 degrees per second, and we can do a similar thing here. Let's set this to 0.2 seconds to start. We do need this to move with the body, and like we did with the torque controller, we need to specify the center axis of the tire. And we'll go with display the vector. Now in this case, the direction very much does matter with this vector. The arrowhead here is showing the direction of rotation. If we wanted to change that, we could either put a negative initial velocity in so that it would rotate in the opposite direction, or switch the signs on the start and end of the Y direction to swap the signs, but that is appropriate. Now if we ran the simulation just with these two motions, the tire wouldn't translate forward. In fact, we can run that and demonstrate that. What we're missing from the motions of the tire is the force controller that would allow the tire to translate in the X direction. So after the tire starts to rotate at 0.2 seconds, you'll see that the tire actually doesn't translate forward at all, even though it engages with the particle bed. See that tire is interacting with the particles, it's rotating, but it's really just slipping. It's not translating forward. So let's stop this, rewind back to 0, save it, and we're going to add in another motion, and this time it's going to be an additional force controller. Now we do get this warning message saying more than one controller on the same body might result in unexpected behavior. It's okay in this case to use two force controllers because we've got the first one limited to the Z direction, and the second one we're going to constrain to the X direction. Now in this case, we're not going to add any forces in the X direction, and like we did with the torque controller, we'll enable it for all time, starting at 0 and ending at 9,999. We won't include gravity in the calculation. We could add damping if required, and I think it's reasonable to include speed cap if you'd like, or we can leave that disabled. Now if we save this and run it, what I would expect to see now is after the tire comes the rest, or engages with the particles from the vertical load, and the rotation starts at 0.2 seconds, the tire should then start to translate in a negative X direction. Now in the response of the tire, in this case, we've got a constant rotational speed and the velocity is going to vary, whereas the previous motion that was set up, we have a constant linear speed and the rotational velocity would change. So again, we're seeing the tire move as we would expect. So we can stop this, and again, that's how to define the motion where we're controlling the rotational velocity. Now the third and final option that I'll cover on how to set up a unique tire motion is a torque limited rotational velocity. So if we rewind this back to 0, again we're going to use the same force controller to apply the vertical load, but in this case we're going to eliminate the constant rotational speed so that we don't have a fixed rotational speed, and instead I'm going to add in a torque controller, and this torque controller is the same as the original torque controller that we set up. We need to specify, in that we need to specify the axis of rotation of the tire, but we will also specify a torque. So let's say that this torque is going to be 1,000 Newton meters about the y-axis. We're not going to include gravity. We can enable a speed cap of 180. If we don't enable the speed cap and there is no resistance on the tire's velocity is going to continue to accelerate, but linearly with no limit. So if we enable this angular speed cap, this will limit the forward travel speed to, or the rotational speed of the tire also, to 180 degrees per second, so long as there is no load that is overcoming what the torsional load would be on the tire, the 1,000 Newton meters. It's applied to both the y-axis. And we need to specify the axis like we did before, so set that to 1,000 and negative 1,000, and this needs to be at 1,200. Display the vector, we'll use the start point, so it's at the center of the tire, and we won't add any angular limits. So in this case, we've got our vertical load that's going to push the tire down. We have this force controller that's limited in the x direction, and there's no force that we're applying to the tire. And then we also have the torque controller that's acting at the center of the tire, and it will have a 1,000 Newton meter force. So what we should expect to see here is the tire begins to drop and rotate at the same time, because we enabled the torque controller at time 0, though the ramp up may be somewhat slow. And eventually the tire should translate forward once it engages with the particle bed and starts to rotate. Now in this case, I can already see that I made an error in setting up the torque input on the tire. I've got the direction in the wrong direction. It should actually be a negative 1,000. So I'm going to stop that, rewind, save it, and we'll implement a negative 1,000. And why don't we set up an initial angular velocity of 100 degrees per second, 50 degrees per second. Save that and run it. Now we should see immediately right at the start, there's tire rotation. Made the same error twice. Let's set it to negative 50 degrees per second with the negative 1,000 Newton meters and run it. And now we should see the direction of the tire rotation is going in the appropriate direction. And because there's no resistance applied through the force controller in the x direction, the tire will just continue to accelerate because of the constantly applied 1,000 Newton meter torque. Now what we could do is apply some type of draft load to the tire with that force controller in the x direction. Say we could apply some linearly increasing load, and if we did that and that linearly increasing load exceeded the torque that was applied to the torque controller, the tire would stop moving forward, or it would start to slip because of the force in the force controller. So we'll stop this here, and that again is the way to define a torque limited rotational velocity of the tire in EDEM alone.